All right, good morning, everyone. We're about to get started with our public webinar today. The topic is pavement vehicle interaction, quantifying excess fuel consumption for pavement design and maintenance decision. Our presenter today is Mehdi Akbarian. Just a few reminders. If you would like to ask questions during the presentation, please use the Q&A function at the top of your screen. Questions will be taken at the end. Mehdi, go ahead.
All right, good morning, everyone. Can you hear me fine?
I can hear you. They won't be able to respond, but
Perfect.
I can hear you.
Okay,
yep.
Great. Well, welcome, everyone. And thank you, Anne. Like Anne said, we're talking about quantifying excess fuel consumption and how that relates to pavements and, their design and maintenance. So just as a, quick overview and the motivation to why we're doing this, the U.S. transportation system is responsible for a lot of energy use annually and also a lot of greenhouse gases. So it accounts for about 34% of the total greenhouse gases that are emitted in the U.S. annually. And when we're talking about pavements, we're actually talking about, their use phase. And so on the right side on this slide, if you look at it's the life cycle of the pavement. So we start off with some materials that we're extracting, we're processing that, and that becomes a pavement, which we're placing. And when that pavement comes into use, it comes into contact with all the vehicles that are driving over it. And what's actually happening is that this vehicle fuel economy translates to pavement fuel economy. So the pavements that have more positive behavior towards vehicles end up, inducing less fuel consumption for those vehicles. And pavements that have, say, a higher roughness, for example, induce more fuel consumption for those vehicles. So this impact of pavements on fuel consumption boils down into two main mechanisms. One has to do with the pavement structure. So when, for example, a truck is driving over pavement here on the left, that pavement deflects under the weight of that truck, be it really, small and minuscule. It's still a deflection, and there is still some energy that that pavement absorbs from that truck. You can kind of picture this as riding a bicycle on the beach or riding a bicycle on a pavement. It's much harder to resist, go against that resistance of the sand on the beach. Same with walking than it is on the pavement. So the same thing happens because of the heavy weight of the truck to different kinds of pavements, and that induces excess fuel consumption. Another mechanism, like I said, is pavement roughness. So when you're driving on a smooth road, your car isn't bouncing up and down, and there isn't energy being transferred from that vehicle's motion, the vertical motion of the car, that's translated into excess fuel consumption. A much rougher road will induce more excess fuel consumption because the car has to bounce up and down, and there's energy that's lost in the suspension system. Whereas on a smooth road, you don't have energy that's going into the suspension, and that's not causing excess fuel consumption for us. So what we do is we take those deflection or properties or the structural properties of the pavement, and we take the roughness properties of the pavement, and we translate them to some excess fuel consumption for different vehicle classes and different roads. And that translates for us into economic impacts or environmental impacts. So whatever we're looking at through the life cycle of these systems. So let's talk about deflection-induced PVI. One thing I should note is that roughness-induced PVI has been studied extensively, and there are models out there that are accepted, for translating a certain roughness of a road to a certain level of fuel consumption for different vehicle classes. It's been studied more and it's been understood more because there's generally a few parameters that describe the relationship of roughness with fuel consumption. So there's the parameter of the road roughness itself, and there's the parameter of the vehicle class, and that's pretty much what breaks down the roughness impact on fuel consumption. In contrast, the deflection-induced PVI, which I'm showing here, it's also been studied a lot, but in contrast, there isn't a lot of acceptance around the magnitude or the level of its impact. So here in this figure, I'm showing studies that go back to 1982 and as recent as 2013. And what they've done is they've taken cars and trucks and they've driven them on asphalt pavements, and they've driven them on concrete pavements. So since, you know, a main finding for a lot of these studies is that asphalt pavements induce more fuel consumption for a lot of cars, that reference line of 0 here is the excess fuel consumption that they were measuring on concrete pavements. And whatever is in addition to that is what they were measuring on asphalt. So I'm not going to get into much detail about the speed and the different kind of distribution, but what we see is that there's almost an order of magnitude difference in what these studies are suggesting as the impacts of pavement type on fuel consumption. So the reason for that is they weren't considering what thickness or what structure of asphalt pavement they have or what thickness or structure of concrete pavement they have. It was just, is the surface type asphalt or concrete? So that doesn't really describe the structure that well. And also knowing that this structure, interact very differently given different temperatures or different speeds. So what we thought we would need is that model that translates, unlike roughness, all the parameters that define the vehicle load and the vehicle speed, parameters that define the pavement viscoelasticity, its thickness, its modulus, and the ambient temperature or the pavement temperature. So all those parameters have to come into a model. And what I'm going to present today is how we developed that model and what are the implications of this pavement vehicle interaction. So the different elements of my presentation today will be around the development of this model for defining pavement vehicle interaction and its, the deflection impact, how we validate that model and the work that we've been doing around that, and the work that's still ongoing. I can talk about that too. We have implemented these models that we've developed for projects and for networks, and they have different implications, and I'll get into that and the sensitivity of these models. So before I start, I'm going to jump into the takeaways and, center my presentation around these. So the first takeaway is that we can actually quantify this excess fuel consumption, be it for roughness impacts or for deflection impacts. We can quantify it with enough confidence to be able to make judgments based on our modeling. We find that excess fuel consumption is quite significant when we compare either the excess fuel consumption cost compared to the investment that we have to make initially to either rebuild the pavement or fix the pavement, or when we compare the life cycle impact of recreating a pavement versus all the losses from that excess fuel consumption and that excess greenhouse gas emissions. Another finding is that both the surface properties, which induce roughness, and the structural properties, which induce deflection, induce fuel consumption, both of them matter, and they matter differently in different conditions, and I'll talk about that context sensitivity. And lastly, I'll show how we can use this excess fuel consumption, given that it's a really important metric, to improve either pavement design or the maintenance decisions that we make throughout the life cycle of a pavement. All right, let's talk about model development. So I'm not going to get into the depth of the equations. If there are questions, I'm happy to answer them. But the parameters that we have here are here on the right. So like I said, there are many parameters that define what a vehicle behaves like and also what a pavement structure behaves like. So these parameters include vehicle load, the speed, the relaxation time, which has to do with the viscoelasticity of the top layer, so asphalt versus concrete, for example. The thickness of the top layer, the stiffness of the top layer, the stiffness of the subgrade, and also geometric properties about the pavement width and the ambient temperature or the pavement temperature. So all these parameters define our pavement vehicle interaction as far as the structural dissipation goes. So we have created this model that has a few different properties, but the main three advantages that I want to talk about is that because it's a mechanistic model, it allows us to come up with scaling relationships between the dissipation or that excess fuel consumption and the parameters of PVI. So that scaling relationship is what I'm showing in this equation up here. And what it defines is that our dissipation form, or dissipation, either in dimensionless form or in terms of the dissipation itself, that delta E, is related to the vertical load, but not just linearly with a square 2 relationship. And it's related with an inverse relationship with the stiffness, the thickness, and the subgrade stiffness. So top layer stiffness and subgrade stiffness. So what this means, what this relationship means, is if you increase the load of a vehicle by 2, the amount that you're increasing that excess fuel consumption is by 4. So there's a power 2 between the load and the dissipation. Similarly, if you increase, for example, the thickness of a pavement, you decrease your dissipation to a power minus 3/4. And then if you increase the modulus of elasticity, that has a negative impact. So increasing the modulus of elasticity decreases the dissipation. And improving the subgrade properties through K will reduce dissipation again. So kind of a relationship, but what it helps us do is figure out what is the most important parameter that we can influence to change the excess fuel consumption. So either within the structure of the pavement or within the vehicle. Solving the equations for calculating this excess fuel consumption is not super simple. So what we did in order to make it simple for either use in life cycle assessment or life cycle cost assessment or general engineering assessment of a pavement's life cycle footprint, we created a large fit of all the possible pavement scenarios and vehicle scenarios that exist and made a fit to it. So this fit is just a simple one-line equation that you put into Excel, and based on those parameters up here, it gives you that excess fuel consumption that you're interested in. And the last importance of the way we have set up this model is that because it's dimensionless, we can scale the PVI phenomenon. So the dimensionless properties of equations have been used to scale, for example, a jet down into something that can, a model that can be put into a wind turbine or something like that, a wind tunnel, excuse me. And we are doing a similar thing. We're using a dimensionless analysis or dimensionless relationship to downscale this phenomenon that's on a scale of asphalt and concrete with, 7-8-inch pavements into something that we can work on in the lab. An important finding that I want to show about the implications of different pavement scenarios or different temperature conditions is shown in this graph. So on the vertical, on the left side, I'm showing the excess fuel consumption, and on the right side, I'm showing the temperature. And these are data from California. So throughout a year, we have the temperature changing from around 5 degrees Celsius to 20-some degrees Celsius. And the impact of that on excess fuel consumption on asphalt concrete pavements or Portland cement concrete pavements is shown here. So AC is the asphalt and PCC is the concrete. And we see that asphalt, because it's viscoelastic in nature, it has a high impact, dependency on temperature fluctuations. So that excess fuel consumption is really dependent on the temperature here. So if we were looking at, for example, Colorado here or some other cold state, we would see that generally the excess fuel consumption doesn't really matter between asphalt and concrete because it would be much lower. But in this case, or in the majority of the U.S., we've done national studies as well, we see that asphalt is highly temperature dependent on temperature changes. And it's also dependent on speed changes. So when a car is driving slower, it has a higher excess fuel consumption than when it's driving faster. But these are the things that our model is showing, and we need to validate that for a real, physical pavement model. So a pavement is defined by some structure that has multiple layers, and these layers are generally they can be categorized or grouped into certain definitions. So here on the left, I'm showing some representations of what we would expect to see in the U.S. network or generally from roads as a structure. So we have a top layer that is either bound asphalt, concrete, or a mix of both, a composite section. And then that's sitting on some soil. And that soil is either, compacted or treated with cement or asphalt. But it's generally in an unbound base or a sub-base or subgrade. So we're taking this two-layer representation of a pavement in real life, and we're creating an experiment around it, which I'm showing on the right here, which is two layers of polymers sitting on top of each other. And what we have a wheel that's, moving at a constant speed like a wheel of a truck or a car would. And what we're measuring is the resistance against the motion of that wheel. Excuse me. I'll come back to this. So what we're trying to measure is the resistance against that motion of that wheel. And this resistance, like in the real scenario, which is, translated into excess fuel consumption, is defined by all those vehicle and pavement parameters. So the horizontal force is what defines our excess fuel consumption. Then the wheel load is what we, simulate in our experiment. We have the vehicle speed, which we simulate as well. We have different materials that define different relaxation times. So we have materials that are highly viscoelastic, more like asphalt, and intermediate materials, and then materials that are almost elastic, more like concrete. We have worked on a variation of top layer thicknesses to investigate its impact on excess fuel consumption. And our different materials give us different top layer moduluses. And we generally have one typical subgrade that we run our study on. So what our experiment is that wheel being moved back and forth on different pavement types and pavement thicknesses, and we're measuring that resistance to the motion of this wheel. Here in the video, there's a little bump, but generally, we worked with one thickness across back and forth. A nice thing about doing this experiment indoors rather than taking a truck or a car outside is a lot of those external parameters that we haven't even included in the experiment are controlled here. So the pavements all have, very smooth surface, so there's no impact from roughness. There are no temperature changes within the lab. We have, the lab is very temperature controlled. A lot of the other parameters, like the weight of the truck, the wind, winds that would change the fuel consumption in a real study. A lot of those impacts from tire and so on, they're neglected by recreating this PVI phenomenon in the lab. And if you were to upscale the size of this wheel and all the, the back and forth testings that we have done on all these tests, it would be equivalent to a study that drove 180 miles by varying all these different parameters in real life. So that's a benefit from scaling this experiment down. Another benefit is because we're using polymers here, we can actually look through some of them. So some of these polymers are transparent and they're bifringent. So we can use a polarizer setup, so to use photoelasticity to look at the stresses inside these materials. So the setup is shown here on the right, upper right, where it's made up of polarizers and filters and so on. And on the left, you see the wheel moving back and forth on this pavement. And it's changing direction quite often. And what it shows is the stresses inside the material. So you see that there's, in the stills on the bottom, there's a higher body of stresses on the left side of the wheel here, which is in front of the wheel and behind it. And here, when the wheel is moving to the right, you see that there's a higher body of stresses resisting its motion. And you can see that really clearly switching direction in the video. When the wheel is stationary, everything is symmetric. But it's that combination of viscoelasticity in the pavement and the motion of the wheel that creates an asymmetry in the pavement response. Aside from being able to look into the material and kind of see the stresses and the dissipation really representing itself, we can also measure those horizontal forces that are resisting the motion. So here I'm showing a set of experiments, the results for, on the vertical we have the rolling resistance force, which is that force that's resisting the motion of this wheel. And on the horizontal we have the vertical load, so the wheel load that's applied, and it's shown here in this figure too. So we did measurements of that horizontal resistance against the vertical load at different vertical loads. So here you see the vertical load going from around 4 newtons all the way up to 30 newtons. And there's a regime that changes between all these points. So this is for one pavement structure and different loads and one speed. So one thing that we see across all the points is that common cohesion force, which has to do with the contact between the tire or the stickiness between the metal wheel and the pavement surface. Something else that we see, which we expect, is that normal friction force. So each one of these layers is going to have some relationship between the vertical load and the horizontal friction by that general definition of normal friction. So some coefficient of friction times the vertical load. And what we see is that we also get some excess rolling resistance or resistance force that is not defined by our cohesion or the normal friction. And that's what we call the deflection-induced PVI, and that's what we define as the energy that's dissipated in this viscoelastic system. So up to some point, we see that there is a sharp increase of the rolling resistance force given the vertical load. And then something happens, and then again, there's a transition zone back to a heavy frictional sliding. And what happens here, if I were to compare this experiment back to real life, is as if a truck was driving over a pavement and indenting that pavement or digging into that pavement at least 3 or 4 inches, which is not realistic. And that is what happens in our experiment here. So around this 15 Newton load, the tire is so deep that the indentation or that deflection is almost equal to the size of that tire itself. So that's why we get a heavy frictional sliding and we don't have that beam representation anymore. So something that we find we did around 200 experiments by varying the load, thickness, speed. And what we find is that through our experimental validation or our experimental setup, we can see a relationship between the dissipation with speed to the power minus 8, almost 0.9, load to the power 2, and thickness to the power minus 0.6. And that is really close to what our mechanistic model was predicting, which is speed to the power minus 1, load to the power 2, and thickness to the power minus 0.7. Something that I won't get into detail here is that this mechanistic model, the actual, speed exponent actually changes somewhere between 0.9 and 1, and minus 0.9 and minus 1. So there is some range that is more in agreement between our experiment and what we're seeing through our model. Because our model is dimensionless, we can also put all of these points on the same plot. And we do that by comparing our experimental results, which are shown for the dimensionless dissipation on the left, and the model predictions, which are shown on the right in dimensionless form. And we see that these, the bullet points or the markers, which are our experimental data, agree with the dotted lines, which are our model prediction quite well. This is in the high viscoelastic case, and we see the same thing for the moderate viscoelastic case, that our model and the experiments agree quite well. And then in the quite elastic case, which represents some kind of concrete pavements, we also see a good agreement between our model predictions and the experimental findings. So this was a validation from a laboratory experiment, and there's also a validation effort going on with, in California with Caltrans, where they're actually taking cars and trucks and driving them on pavements. And we're involved in that in the modeling and in the comparisons with a couple of different universities. If there are questions about that, I'm happy to address that as well. So this model that we've validated on the experimental level, we actually calibrated based on actual pavement data, and we use it in project level implementation. And let me get into what I mean by project level implementation. So generally, when we're looking at a life cycle of a pavement, we just start with some pavement structure that we think is right for the traffic that it's going to carry. And we use these principles called the mechanistic empirical design principles to figure out, is this pavement good enough? Is it going to handle that traffic good enough or not? And if it's good enough, then we create some bill of activities which define how much material goes into the pavement structure, how much work goes into creating that pavement, and how much those things cost through life cycle cost assessment, which is at LCCA, or what are the environmental implications of all these decisions that we're making. And then we figure out, is this adequate enough, and figure out is it good environmentally and cost-wise. Now, what we're trying to do now is actually bring that evaluation of life cycle cost assessment and that environmental assessment into that performance judgment. So that adequacy of performance has to be something that meets the demands of the traffic, but also meets the cost demands and the environmental footprint demands of either the community or the DOT or any agency that's looking at these roads. So again, we look at all the material quantities that go into all these steps, the construction activities that happen, when they happen, what are the things that have to be decided on, and then we figure out how much money goes into this life cycle and how much emissions come out of these practices that we're implementing because of this pavement design. So we run these scenarios for many different pavement cases. So for example, here I'm showing the impact of life cycle cost assessment for a pavement scenario that we studied with Minnesota. So here we have a concrete pavement and we're looking at the life cycle costs. So we see that the majority of the costs are dominated by that initial investment on the pavement. So and then there is some maintenance cost for that pavement, but it's around, it's around 16%, let's say. What's interesting is that the cost that's applied to the user because of the quality of these pavements or because of the traffic that they have, because of the traffic delay that they have to meet due to maintenance, for example, that is equivalent to the maintenance cost as well. So there's some findings that's important for this study. And we see the user costs kind of, are important when we compare it to the other costs that the DOT acquires. When we look at those user costs, however, we see that majority of it has to do with the excess fuel consumption, and very little of it has to do with traffic delays. So again, that excess fuel consumption is an important part of the life cycle cost assessment, for example. We see this again with life cycle assessment. So when we look at the environmental impact, we see that there are cases where the use phase really dominates. So the use impacts from that excess fuel consumption, from all the fuel that's burned, from some of those, delays, that's more significant than the initial investment that we're making or the maintenance and rehabs that we're considering. When we look at the breakdown of that use phase, we see that some of that contribution of fuel consumption has to do with the deflection of those pavements, and some of it has to do with the roughness of those pavements. We look at some other scenarios, and it's the other way around. Sometimes a pavement is rough, but the structure is good, and sometimes the structure is not so good, and the smoothness is pretty good. So there are different scenarios where the deflection and the roughness part of the PVI play different magnitudes in analysis. So just to get a sense of how that will work out in a U.S. network, we did some studies where we looked at the impact of the excess fuel consumption given different locations, different traffic levels, and different pavement designs. And again, we see that changing behavior between the use phase and that initial investment that we make. So there are cases where the traffic level is high. For example, here we're looking at an interstate with a rigid design, and we see that that use phase comes out to be significant, either roughness or deflection impacts. There are cases, where use phase is smaller than the initial. So here again, that darker green on the upper right is use phase, and the lighter green is the initial. And similarly, when we go around the U.S. and we look at different scenarios, we see that these percentages and the importance of one to the other really changes. So that really becomes important when we're looking at a roadway network. You know, when a DOT is trying to make judgments about where to invest their money, which roads are the worst ones or which ones are the better ones. So I'll bring that context dependency of this excess fuel consumption from different project levels back into a network level and see what the implications of changes in the network are for these PVI models. So when we're talking about network, we're talking about a lot of data. So we have to put all this data together to recreate all the changing scenarios that we're going to expect. So some of the changing scenarios, one of the data is pavement roughness. Pavement roughness could change on a the road-to-road basis and also on an annual basis. So those are all input into the roughness-induced pavement vehicle interaction model, as well as traffic levels. So we have the total traffic levels and the truck traffic levels. There is difference in response of each one of these vehicles on fuel consumption. And then we also have information about speed for each one of the lane miles of a roadway network. So all of those information go into a roughness-induced PVI model. And then some of that, along with material properties for each one of these lane miles, the monthly temperature for the different locations that the roads are spread through, the thicknesses of these layers, and the types of these pavements go into a deflection-induced PVI model. And that gives us a snapshot of how our PVI system, how our network is doing as far as inducing excess fuel consumption for cars and trucks. So we did this with Virginia. We also did it with California. Here I'm showing the bigger study that we did was with California, and that's why I'm showing it here. And there are really interesting things that come out of a study like this. So here I'm showing the excess fuel consumption added for cars and trucks on the Caltrans network. So the Caltrans network includes interstate. It also includes some lower level roads that are not very high in traffic volume, for example. So what I'm showing here is that excess fuel consumption in liters, and the greens are where the excess fuel consumption is low, and the red is where the fuel consumption is quite high. And you see that we see a lot of red around the city centers, so around LA and also around San Francisco, which is something we expect. We have a high level of traffic there, and we expect to see a lot of excess fuel consumption given whatever road conditions that we have. Something else that pops up is the main interstates that connect the north to the south. Again, we see the traffic volume is quite dominant here, and that is actually due to truck traffic, and we see the impact of that also with roads that lead out of California into the neighboring states, either on the northern side or the southern side. But we can look at the map and talk a lot about what is important, but overall, when we look at the excess fuel consumption that happens on Caltrans' network, it's around 21 million liters of excess fuel, or excess fuel that's due to PVI. And compared to how much fuel is used on Caltrans' network, that's around 2.5%. So just the state of these roads is inducing around a 2.5% increase in fuel consumption. This excess fuel consumption is important no matter kind of what metric you look at it. So for example, CO2 is right underneath around 2%. NOx is a health a factor that's really important for kind of health impact. So is particulate matter, so NOx and PMs. And those are only emissions that are coming out of diesel trucks or diesel fuel. And we see that, for example, particulate matter 2.5, which is really bad for human health, kind of respiratory problems. Just the condition of the roads is contributing 4.4% increase in those impacts within California. So that's quite significant, and there are ways where we can use this information about which roads are worse for excess fuel consumption and human health impact to fix them. And there are different ways we can do this. So let's assume that we had enough money to maintain or rehabilitate about 1% of the network, which is what I'm showing on the left side here in that table. So the network impact reduction, we have enough money to do 1% maintenance within this network. We can select the roads that we're going to maintain randomly. For 1% effort, we're going to get 1% return. We can select them based on how rough they are, which is a typical practice in a lot of states. So roads that are very rough get maintained first, and then roads that are smoother kind of wait until they get rough. And this is what I'm going to bring you along to the graph on the right. So on this graph, I'm showing the vertical on the left. I'm showing the excess fuel consumption that we're seeing in California, and it goes up to about 700 million liters for this network. And on the horizontal, let's just look at the bottom horizontal, I'm looking at the required network maintenance to bring this excess fuel consumption from that 700 million down to 0. So if we maintained every single mile, which is 80,000 lane kilometers, around 50,000 lane miles, we would bring all that excess fuel consumption down to 0. We have different paths to take, this route. One was that we would select our roads randomly, which is orange line here. So if we select, let's say a 20%, we have enough budget to maintain 20% of our network, we get 20% response or return from that random selection. That IRI selection that I was talking about, where a lot of states do it, is a green line on this graph. So for 1% maintenance and rehab, we get 3.3% reduction in our excess fuel consumption. There are better ways of selecting these roads, though. So we can select a combination of roughness and traffic volume and have that be our metric. And we see that on a 1% investment, we get 4.7% return. I'm not going to get into all of these, but excess fuel consumption, which was the metric that we defined as the one that has all the possible information that we can kind of gather from DOTs and put into these models, has the most resolution, or is the best one to make judgments around the use phase. So when we spend 1% of our money, we get a 6.8% return on reducing those use phase impacts, or kind of eliminating those use phase costs. So that use phase, just given its importance within the life cycle, is a really good descriptor of what roads are good and what roads are bad and where we should invest our money. But it's not the whole picture. There is a level of spending that has to go into that road to bring it into good condition. And there are roads that have good, high demands for that expenditure, or they have low demands. And it's hard to make a judgment just by looking at that excess fuel consumption. So we've developed models and are currently working on, enhancing them with a couple of different states, where we take that information about the current state of the system, as I described, for example, for California, and we take all the available maintenance actions that we have open to us. So, for example, overlaying a pavement or tearing it up or doing whatever to that pavement to make it last a couple of years longer or a long while. And we can project how these different activities that we do on these pavements will last. So some will last a couple of years, some will last many years, and we can look at that through kind of a deterioration model perspective. And we can also look at the prices and how they develop over time. It's not just about the pavement condition, but it's also about, if I make a decision to do something 20 years down the road, is that going to cost a lot 20 years on the road, or is the cost going to be quite similar to where we are at now? And lastly, each agency, each DOT, they have a set of objectives and goals that they have to meet. So these could be around, the quality of the pavements, where they say, I want 90% of my pavements to be great. or I want, at least, like at most 10% bad roads or something like that. Or I have a $50 million budget and that's it, So these objectives and goals also have to feed into our model. And that's what we call an allocation support tool, where we have some goals and we try to maximize our expected performance. And that's how we select projects to improve the overall return from an investment. So with that, I'm just going to come back to our key findings again and kind of frame the presentation so that if you have questions, we can go back to it. So again, the main finding is that we can quantify this excess fuel consumption, both for roughness and deflection, well enough to make judgments, either at a pavement section network or pavement section level, so project level, or at a network level, where we can compare pavements against each other and say, this is a better pavement for this job, or here we don't have a lot of traffic, maybe we can do something else. Anyway, we saw that the excess fuel consumption is significant on its own when we compare roughness and deflection, when we compare cost or environmental impact. It's just like something big that has to be considered either through policy or through engineering. We saw that both surface and structure mattered, so that's roughness and also the the deflection or stiffness of the pavement. And lastly, that this excess fuel consumption, given its importance and given its role within the life cycle of the road, can really be used as a management metric to improve the design and maintenance of these roads, these decisions that DOTs and agencies have to make. So with that, I'll just open it up to any questions that you may have.
Thank you, Mehdi. As a reminder, if you have questions, you can enter them via the Q&A window or the chat window at the top of your screen. And we do have one question, Mehdi, to start. One of the participants is wondering about the relationship between tire pressure and pavement stiffness and whether pavement deflection can be offset by higher tire pressure.
I'm trying to read through them. So that's a great question. And I'm going to run into some secret slides that I have prepared. Let's see if my computer allows me. All right, so we have to go through all the slides together because it's not letting me get out. All right, so that's a great question. And I'm going to bring up a more detailed view of the different mechanisms of pavement vehicle interaction. So don't mind the text. Let's just look at the figures on the right. We have pavement texture, which has to do with the size of the aggregates of the road, and it really deflects and changes tire and dissipates energy in the tire itself. So that spring and asphalt system that you see in the tire is where the energy is absorbed. The same spring and asphalt system that absorbs energy is also in the suspension system of the car. So, and it's really, activated when the car is driving on a rough road. And then the last step is when the spring and asphalt system is in the pavement itself. So when we're talking about texture and we're talking about tire impact, we're just talking about that uppermost figure where it has to do with the tire properties and the energy is dissipated in the tire itself. So when when a tire is more inflated, it has different spring and asphalt properties. So the dissipation properties in the tire have changed. So if that same car with higher tire pressure is driving on a pavement, it just sees less fuel consumption because the tire's properties have changed. Now, if a tire is sitting on a pavement and it has low tire pressure, it has a larger footprint on that pavement, and if it has a high tire pressure, it has a small footprint on the pavement. So we did a study of the impacts of that footprint, which is shown on this upper part with A, that spacing within that spread of the load. So we did a study of what is the impact of that footprint on the dissipation in the pavement. And here I'm showing the dissipation rate for many different speed scenarios and many different tire sizes. So that there's an order of magnitude change in the contact area of the tire. We never have that, with a normal tire. You never change the contact area by an order of magnitude when you inflate it, like in real life scenarios. But still, we see that all those tire contact areas, from the narrow tire, which is 0.2 meters, to 2.1. I'm sorry, this is not an order of magnitude. But they all fall on the same line. And there isn't much difference in that dissipation rate given the tire contact area, or in other words, the tire pressure. So tire pressure does have a big impact. It's on the texture scale, not on the deflection or structure of the pavement scale. Does that answer the question? I hope.
I don't see any follow-ups. I think so, but of course, if there is a follow-up question to that, please feel free to submit it via the Q&A. Let's see, next question. On about slide 19, so if you can find slide 19, you were showing a plot and indicated that it shows that the model is forecasting close to actual performance. The number of points were limited. Have you extended the comparison to more comparison points?
Yes, you're right. The number of points is limited on slide 19. So to answer the two questions, I'm going to answer the second one first. No, we haven't extended the study on any of these materials. So I know there are like 4 points here, but this is a collection of many experiments that have boiled down into 4 dimensionless points on this graph. That's one thing. And the second thing is, in this elastic case, or this elastic material, it was really difficult to create this sample. So if I show one of these samples, and excuse my computer that is not letting me jump slides. Give me one moment. Maybe it did. Okay. All right. So this kind of shows the samples. So the samples are about 4 meters long each. So here you see one sample, from here all the way to the end of this long bench that we have. And I had to pour each one individually in, there were many limitations with pouring of these samples. I don't have the right slide, but just because of the size, we couldn't put them in the oven, for example. So there were more limitations on the elastic case, for example, which are these 2 green ones on the right. So the 2 results in 4 points, and the 3 results in, I think, 8 or 9. But yeah, that's quite the answer. That it was quite difficult to create more points for those.
Thank you. So the next question has to do with environmental impacts, and the question is, in which case studies did the CFC dominate the results and why? Or perhaps you can, yeah. Mm-hmm.
Can you repeat that again?
So it says, in which case studies did the CFC dominate the results and why?
All right, let's go back to one of those figures so we can compare. I don't know if you're talking about the maps or the individual cases, but I will talk about the individual cases, and if we hear that it's the maps, I'll get into that.
He's saying yes, the map.
The map. All right, great.
Yes.
Thank you.
Thank you.
All right, so let's see. Let me put some of these slides together so I can. All right, great. Yes, so there are some indications that we can kind of follow and see what was happening in different regions. So, I said that there's a lot of excess fuel consumption around the cities. So here on these 2 maps, ADT is the total traffic volume, ADTT is the truck traffic volume. So there's an indication that, the route that has a lot of trucks on it or around the cities, there's going to be a lot of excess NOx or particulate matter emissions, and also like greenhouse gas emissions. Or where we have a lot of passenger or total traffic, which is dominated by passenger car traffic, we have a lot of impact, again, around the city centers. So that's one indication. Another indication that we have is the climate zones. So California has many unique climate zones within it, that go from quite hot to cold. And given where you are, so if you're in the cold climate, the deflection-induced PVI would be smaller, would have smaller impacts than if you're in the hot climate. So that's one indication of the climate zone impact. And then on the left side here, we have the roughness. So where you have high roughness, you would expect to have high excess fuel consumption from roughness in these cases. So we can kind of follow each one back and see why it happened. But let me step back and just talk about deflection and roughness-induced PVI. When there's high load and high temperature and low speed, deflection-induced PVI dominates. When there is high roughness and high passenger car traffic volume, you have high roughness impact. So it kind of boils down into two. Passenger cars are not much affected by deflection-induced PVI. Trucks are highly affected. Trucks are minimally affected by roughness, not minimally, but less so than cars, and cars are highly affected by roughness. And the reason behind that roughness thing is you can just think about cars are built to absorb the, that bouncing of the car or that energy that's transferred from a bad pavement to your back. But a truck is not built to do that. So a car is built to absorb all that energy so that you don't have a bad ride. But a truck, it is really uncomfortable in the back of a truck. Yep.
Okay, thank you. That's all the questions that we've received via the chat, and I just want to note that we're getting close to time. So if there are additional questions, we will be posting this video to our YouTube channel, and we'd welcome questions there or via our Facebook page or Twitter. And of course, feel free to email us as well. A couple of notes. Mehdi did recently publish a research brief on the Minnesota case study that can be found on the homepage of our website. And our next public webinar will be August 10th on a building LCA topic. So hope you can join us there. And thanks again to everyone for joining us today. And thank you, Mehdi.
Thank you, everyone.
Have a great day.